Welcome back, Chem 51, to our Week 5 pre-activity lecture. This lecture covers 4.7 in McMurray and Activity 43A in the lab manual. I would like you to read them before and after, but you need to understand that they have different methods of drawing Lewis structures, and I also have a different method of drawing Lewis structures. So I'd like you to look at both and stay open-minded, and you can pick a method that works for you. But I and my students have had success in the past with the method I'm about to show you. So we're just going to start in with an example. Step one, doing this for water, H2O. And the step one is to determine the collective number of valence electrons contributed by all atoms. So I have one oxygen, and that contributes, it's in group 6A, so 6 electrons. Okay, and so I have two hydrogen, and with 1 electron each, and so I get 2 electrons here. And so 8 electrons available. Okay, so our next step is to choose what's going to be the central atom. Okay, and what you're going to choose is the atom that is the farthest away from fluorine except hydrogen. Okay, so I have to pick oxygen, and I'm going to arrange the other atoms with single bonds. Okay, now I need to obey the octet rule. And so I'm going to add lone pairs wherever I need them to make sure each atom is satisfied. And for the moment, I'm going to ignore how many electrons I actually have available. So I'll put 2 lone pairs on the oxygen. So it has 8 electrons, with each bond representing 2 electrons. And the hydrogen, obeying the duet rule, has 2 electrons within that bond. So everyone is happy here. Now on step 4, let's go back to reality. And we're going to count the electrons in the drawing to make sure it matches the number of electrons that you have available. So I have 8 electrons available here, but I have 2, 4, 6, 8 electrons in my drawing. So that's okay. 8 electrons, okay. And so if your numbers match, then you do not have to move on to step 5. Okay. But let's look at an example where you do have to go to step 5, and that is CH2O. So I have 1 carbon, and that gives me 4 electrons. I have 2 hydrogen, and that gives me 2 electrons, and then 1 oxygen, and that is 6 electrons. So I have 12 electrons available. Okay, so let me choose my central atom. It's we're ignoring the hydrogen, of course, so it's between carbon and oxygen. Carbon on the periodic table is farther away from fluorine, so it must be the central atom. Okay, I'll arrange everything else using single bonds and go from there. So now we have to obey the octet rule, regardless of how many electrons I have available. So let's draw the same thing with the lone pairs necessary. So my hydrogens are fine. They have their 2 electrons within the bond. My oxygen needs 3 lone pairs, and my carbon needs 1 lone pair. So let's count up these electrons. We have 2, 4, 6 electrons in the bonds, and then we have 8 electrons in lone pairs. So that's no good. But let's remember in a covalent bond, if we need multiple bonds, we can get rid of 2 lone pairs in exchange for one multiple bond. So let's show that mechanism. This one is going to go in here. This one's going to go in here. This one's going to leave. And this one's going to leave. So you've just lost 2 electrons. So let's draw the final structure. Now I only have 3 things coming off of that um, central carbon, so I'm going to draw these as far away as possible from each other. Remember, like charges repel, and since bonds are made of electrons, they are negatively charged. They're going to push away from each other. So these are the 5 steps, sometimes 4, sometimes 5 steps, to drawing the Lewis structure of a neutral molecule. Now let's look at polyatomic ions. We remember this from our naming chemical nomenclature activity. So we have NH4 with a positive charge. So first step, determine the number of valence electrons, just like before, and then I'm going to add or subtract an electron based on the charge. So I have 1 nitrogen, and that equals 5 electrons. I have 4 hydrogens, so that's 4 electrons. Now that's an odd number of electrons. That's kind of hard to deal with this model, with this Lewis structure model. So positive charge, though, we have to take away an electron. Okay, so we only have 8 electrons available. Okay, so moving on to step 2, since I only have one option that's not hydrogen, I will choose the nitrogen as my central atom. Okay, I will draw my hydrogens as far apart from each other as possible. And with step 3, it doesn't look like we have to do step 3 here. Um, the nitrogen has four bonds, so it's surrounded by eight electrons. The hydrogens have two electrons each from the bonds, and so we're going to say Na for that one. Now let's count the electrons and see. We have in each of the bonds 2, 4, 6, 8 electrons. So this is great. So the only thing we need to change about this to make it proper is we're going to put it in brackets and draw the positive charge outside. Okay, and so we do not have to move on to step 5. That is Na, which I forgot to take out. Okay, so let's look at another example where we do have to go to step 5. So I have one nitrogen giving me 5 electrons. I have 2 oxygen giving me, so it's 6 electrons each. So I have 12 electrons. And then the negative charge, that will give us 1 additional electron. So we have 18 electrons available. Okay, so let's choose nitrogen as our central atom. It is the farthest away from fluorine. We're going to put our oxygens evenly spaced away from each other, attached with single bonds. Okay, we can see that the octet rule is not satisfied for anybody. So let's draw this again, but with the lone pairs that we need. So each oxygen will need 3 lone pairs. This nitrogen will need 2 lone pairs. Okay, let's count up our electrons. We have 2, 4, 6, 8 around the oxygen, 2, 4, 6, 8 around the other oxygen. That makes 16, and then 18, 20 electrons. So that's 2 more electrons than we want. Okay, so we need to have multiple bonds here. So let's show it. We only need to get rid of 2 electrons, so that's only 1 bond we need to get rid of, or that's only 1 pair that we need to get rid of. Those 2 are going in there. Those 2 are going away. And then we have one double bonded O and 2 lone pairs, or 2 electrons, 1 lone pair on the nitrogen. We still have 3 lone pairs around 1 oxygen, and then 2 lone pairs on the double bonded oxygen. Now we can see that there are only 18 electrons represented in this drawing, and the octet rule is satisfied for all atoms. And so let's do our final step. Because it is an ion, we're going to put it in brackets and put the negative charge outside the brackets. Now let's look at a concept called resonance. You may have noticed that there are 2 oxygens in our nitrite molecule, or our nitrite ion, the NO2 minus. And it doesn't really matter which oxygen that double bond is on. And so this is called resonance. Okay, and resonance occurs when there are multiple plausible Locations. Sometimes there are locations that are not plausible. So it's multiple plausible locations for an electron pair. And this can be a bonding pair or a non-bonding pair. So let's take a look at the NO2 ion first. So we're going to start with brackets. Anytime you have resonance structures, as well as anytime you have an ion, you have brackets. So let's draw what we had before. Now we'll draw this double arrow. And we have our other resonance structure where the double bond is on the other oxygen. And then we'll close the bracket and put our minus charge outside. Okay, this happens with neutral molecules as well. So let's look at SO3. Okay, so double check to make sure we have 24 electrons represented in this drawing, and we do. So this double bond could be in any of these three places. So we'll draw a double arrow. Oh, I almost drew a hydrogen for no reason. So we have three options here. And it's not an ion, but it is resonance, so we have the brackets. Now, these two examples only showed a difference in bonding pairs. Let's look at an option where you have some non-bonding pairs, and that is our thiocyanate ion. So let me see. Oh no, pardon me, I have to erase this. Carbon is in the middle. Okay, so this is one option. Okay, so carbon is okay. It has four bonds. Nitrogen is okay. It has three bonds and one lone pair. And sulfur is okay. It has one bond and three lone pairs. So let's draw another option. So another option would be this. Okay, so we can see that the octet rule is still satisfied, and we just have a different arrangement of lone pairs and bonds. Okay, and we even have a third option. And we can see that the octet rule is still satisfied. Okay, now one of these options is more plausible than the others. We're not getting into which one it is, um, but it just understands that some resonance structures, when you're moving around non-bonding pairs, there are some resonance structures that will be more plausible than others. And so the molecule, or the ion, will spend more time in that ideal structure. Okay, we're not going to go into details on that. I just want you to keep that in the back of your mind. Okay, so the last concept is bond order, and that is fairly simple. So bond order, it refers to the number of bonding electrons. Bonding electron pairs. I shouldn't have drawn that S. So it's the number of bonding pairs between two atoms. Okay, so the higher the bond order, okay, the shorter is the bond length, and the stronger is the bond. Okay, so a single bond has a bond order of 1, um, fairly straightforward. It typically has a bond length of 140 picometers. And we'll just at the bottom, 1 picometer equals 1 times 10 to the negative 12th meters. So it is very tiny. So it's 140 picometers for a single bond, and that it takes approximately 90 kilocalories per mole to break that bond. And so don't worry about what a mole is yet. It's just a specific amount of molecules. We'll go into more detail later. So a double bond has a bond order of 2, and it's about 110 picometers. But that takes twice as much energy to break. Triple bond has, you guessed it, a bond order of 3. It has the same bond length as a double bond, but it takes 260 kilocalories per mole to break the bond. Okay, that concludes the pre-activity lecture for week 5. Thank you so much for your attention, and I look forward to seeing you in class.